Welcome to the DeviceDojo. I'm Joseph, and this is where we tackle the practical side of securing connected devices, from over-the-air updates and fleet management to the broader challenges like incident detection and response, compliance, encryption, more. Always actionable and hands-on, brought to you by Northern Tech, the makers of Mender. Let's go. Okay, everybody woken up again? Michael will usually tune in now to avoid the noise. And this is a couple of news because this is the first episode where we're not actually talking about something Linux. But first things first. So about the DeviceDojo, this is presented by Northern Tech, which is the makers of Mender.io, the makers of CF Engine. And I am working for them as a developer enablement expert. So I'm helping people, all kinds of developers, internal, external, to get their stuff done. And the DeviceDojo aims to be always actionable, always giving you content that you can pour into your own projects. This so far contains mostly tutorials, and a couple of live coding and office hour sessions will be coming up real soon. So, what are we talking about today? This is the first session, as I said, not on Linux. It is the first session on Zephyr, and they're on a very specific challenge. I've actually got one Zephyr board near me here. This is the one that I'll be using, or its brother, twin, because this one is not plugged in. And first, we're going to talk a little bit about what Zephyr on this thing means, or generally on whatever other device that you have. Then we're going to talk about adding TCP/IP connectivity. From there, going to HTTPS, HTTP, and in the last step, going to HTTPS. And then, of course, I'm going to show you the code and let it run. And as this involves a lot of further information and code, I will also drop you the links for for the full in-depth tutorials. Okay, where are we? Next slide. So, what is Zephyr? It's like one of the big buzzwords these days when you're looking at LinkedIn or whatever open source content that you hope to ingest in the embedded world. And Zephyr is a real-time operating system, and it's primarily aimed at MCU class systems. What do I mean to say by that? So first of all, real-time operating system means that it's meant to meet hard deadlines. This is one of the real big misunderstandings. Real-time does not mean fast. Real-time means the exact opposite. It usually means slow, but it means guaranteed. Real-time means that you know when a certain event will happen. No more, no less. This is what Zephyr can do. And it's meant at MCU class systems. Again, what does this mean? MCU class is your classical microcontroller, which indicates that we're talking about systems with sometimes only a couple of kilobytes storage, either RAM or ROM, a couple of tens of megahertzes. We're not usually not talking about many cores, gigabytes of RAM, all of this stuff. It can run on those. So there's nothing that keeps you from running Zephyr on an x86, on a large one, or on a large ARM CPU, but it's not like the natural habitat. Zephyr has grown tremendously over the last couple of years because it's reasonably easy to add boards or customizations. So at the moment, I checked this yesterday, Zephyr supports more than 900 boards, has more than 50 subsystems, 90 driver categories, and is approaching 2,000 individual drivers. So a driver can be for any peripheral like a data acquisition thing, a networking chip, whatever stuff. It runs on a couple of architectures, and the most prominent ones these days is obviously ARM, but also x86 or Xtensor, which we will be using. It runs on RISC-V, and a minimal ROM footprint, so which in terms of flash that you actually need is in the area of 10 kilobytes. That doesn't give you a whole lot of functionality, but it comes alive with that. The one big thing that is different when you build for MCUs, like you do with Zephyr, as opposed to Linux, is that you do not build like this executable and this kernel and this file system or whatever. If you're building for an MCU class thing, then you usually have your application code plus whatever RTOS or libraries or whatever you want to use for that. You compile all of this and it goes into a singular blob, binary image. You can call it whatever you want. The key part is this is the one thing that needs to be flashed into the non-volatile storage of the device. Usually it involves the startup code, all of the libraries, the reset vectors, blah, 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 blah. All of the data, obviously, this will be important later, that you need to do whatever it is meant to do. And you cannot clearly or easily separate between, hey, this is my user binary and this is the R2S there, because it's just linked into one binary file. This is what we will also end up with. And a very, very introductory part. So there's the Zephyr getting started guide. I encourage everybody to try this one out. So you just build with the West tool. So West is like the somewhat friendly front end to all of this complex build processes that Zephyr supports. Tell West, build for this specific board, build this specific application. Then you can tell West, hey, flash. And in the specific case of the ESPs, which we're using, there is an add-on or a plugin, I think they call it, which is called Espressive. And this supports a monitor command, which will, after flashing, just like dial into the serial terminal. And so you can see the printf and boot logs and whatever. And this is really, really handy. So if you're just trying the hello world thing, then you should see something like this. Booting Zephyr OS and then the hello world. So yay, your tool chain, your device, your everything is working. A device that does only print hello world or blink an LED is not a lot of fun usually. And that's why we're going to finally do something useful with it. We're going to look at connectivity. You might know there's a whole lot of connection protocols, and we will focus, or we want to go to HTTPS. And the first thing that you need if you're going to HTTPS is you need to get the networking stack and interface up and running. On the ESPs, this means getting Wi-Fi up, connecting to some Wi-Fi access point that you happen to have, and obtaining an IP address. Zephyr uses kconfig. This is very, very similar. This is to the Linux kernel. It is derived from the Linux kernel. So you can just define all of the features that you want to add by putting them into the configuration file, like config whatever thing equals yes. These are the ones which are really, really the core of getting Wi-Fi up. So you can see we need to have the networking stack as a whole. We want to support IPv4. This is good enough for now. We want to have DHCP for it. And for the transport layer, we want to have Wi-Fi, and we need to manage Wi-Fi through the facilities that Zephyr gives us. This network management in Zephyr is entirely callback based. So you tell the networking management, hey, here's this event structure. In this case, it's event callback, for example. And tell, okay, this is the callback that I have. If this happens, then go there. We do this for Wi-Fi up. We do this for We do this for IP address obtained, things like that. So we can actually trigger on something. And if we do this, yay, things again through the monitor tell us we're connecting to my network here, which is called NTPAF for reasons, and I can obtain an IP address. So, okay, we have successfully connected this device to a network. Just having the connection obviously is not really productive. We need to actually do something. And here is where the first step seems to be really, really easy. And the second one is super complicated. First of all, Zephyr offers a networking stack with a POSIX style API. I looked up the documentation real hard and it feels a little bit confusing because they call it BSD sockets. If you look at the documentation, they are all super strange prefixed with set sock whatever. And you're like, this is not what I'm looking for. But then if you enable POSIX API compatibility, they also get exposed under the calls that we know and love, like get address info, socket connect, things like that. Stuff that you already know from Linux. And there is a few helpers that you can use to assemble HTTP requests, for example. HTTP in the end is just pushing plain text back and forth. So, I mean, technically you could do HTTPS just with Netcat or with Telnet. And back in the day, we used to do this to verify that a server works, but it's actually not a lot of fun. And it's also not a lot of fun to reassemble strings like these in your microcontroller. So I encourage everybody to not reinvent another HTTP client library, use what already exists. And in the case of Zephyr, HTTP client request exists and we can happily use it. So we need the sockets API. This is what actually gives us the connection. We want to have it in POSIX style, and we want to be able to use the HTTP client. The last thing that we need for a very initial HTTP call is DNS. Technically, I could hard code an IP address and just go, call this IP address. But this has limitations relatively quickly, and it's a maintenance nightmare. Luckily, Zephyr already supports DNS. We just need to enable it, and we need to tell it which DNS server to use. In this case, it's the 8888. It's the Google one. You could also use Cloudflare one, which is 1111, and a couple of other ones, or your local one. I just put in one which I know that you will be able to use too. So we can connect. We have our client set. Now, the final thing we need is something to actually talk to. In your connected device project, you usually do not open websites because, I mean, that's where HTTP actually comes from. You open a website with an index HTML, you can read it, it gives you information, it gives you more links, all of this. But your ESP usually doesn't read websites. In the most cases, you want to talk to some API. And the ones which are very prominent these days are REST, which in the end just means, hey, there is a certain structure to how the endpoint is laid out. There is semantics, how you call it. And I just wanted something that you can call without authentication, without anything, and it will give you somewhat well-formed content back. I went looking, and the one that I found and chose is JSON placeholder.typicode.com with a little bit of additional stuff that is only relevant in the code. But if you look at that site, it gives you free to use endpoints that you can call and then give you just some data back, which is exactly what we want. Because this reflects real use cases very, very well. You create some data or you want to pull data, you call the API, you get something back. It is structured as JSON, as YAML, as XML, or whatever, and then you do something with it. In the code, it looks like this. We just want to use the HTTP GET functionality. HTTP path is the tail that you need on the endpoint. It is documented on the JSON placeholder side, and also in the tutorials and full code section that I'll provide later. You need to give the host, which is JSON placeholder topiccode.com, specify the response, and again a callback once the response has arrived. Again, buffers, because we're not in Linux land or a higher operating system where you can just like malloc or auto malloc and everything gets thrown somewhere. No, you have to be very, very clear and say, hey, this is the amount of data that I am expecting at the most. And you can put it there. And if something bad happens or it goes out of this, well, then error. This initializes the structure, and then we can just call it. And again, I'm running it, and everything goes fine. I get some fake JSON data back. User ID, title, lorem ipsum, blah, blah, blah. But okay, we have connected our device to the internet. We have gotten an HTTP response. All good. So far, it's a little bit of a tinkering, but not super complicated. The problem here is it's pure HTTP is like 90s style and not exactly secure. We could also say it's totally not secure because everybody could pretend they're our endpoint that we're talking to. Everybody can sniff the data. It's basically just, it's like sending a postcard. Everybody can read and temper it. So finally, we want to put the S into HTTPS for security. And the two core aspects that HTTPS offers are encryption. So that once, and this is semi-important, once the connection is established, the content is encrypted. Then nobody can actually tell what you're transmitting. And it's authentication. You know that you're talking to the one you're thinking you're talking to. And this is both good, but also a challenge. And I'll show you why. First, encryption. You can't just say, hey, now encrypt everything. No, you need to have the fitting libraries. Zephyr brings embed TLS for this. Again, you configure it through kconfig. The problem here is, or the challenge is that MTLS, embed TLS, and cryptography configuration are very, very complex beasts. This is just an excerpt because you need to be very, very clear about which cipher suits you need to support, which algorithms, how much stack you need for this, and so on and so on. This is really not exactly trivial. And you can already guess that by adding all of this, yeah, it adds a lot to the storage requirements, both in CPU, both in RAM and in ROM. Heap size is also very important because all of this incoming data needs to go somewhere. So when I said earlier, hey, this works from 10 kilobytes upwards, I guess that we're now in the range of a couple of 100 kilobytes, just because encryption is not trivial. And the bigger challenge, from my point of view, actually is the authentication. If I'm going out there and saying, hey, I want to talk to this endpoint, how do I know that the response coming in is actually from this endpoint? The answer is the endpoint also gives me a certificate. How do I tell that the certificate is valid? Yeah, on your mobile, laptop, server, whatever, where you have a higher operating system, that's completely easy because they already bring you a full-featured suite of CA certificates, like the root certificates that your browser, your system are willing to trust without further ado. And I've checked those. They are in the range of 160 kilobytes, plain text, compressed. So if you extract all of this, you're easily going up into a couple of hundreds. And this is not something that we want to put onto our MCU just for knowing, hey, these are the servers that we trust. Plus, those certificates also get invalidated, new ones get added, old ones get moved out. And so how do we do this on an MCU like that one? The answer is we need to find out which is the one that we are relying on, obtaining it, and then actually putting it into the firmware. In this case, we're looking, you can use OpenSSL to do this. We're connecting to the endpoint, JSON placeholder, topiccode.com, 443. Why 443? Because it's the HTTPS port. We want to have the certificates, and then we are extracting the chain of trust. Chain of trust means that TypeCode, for example, is not a root certificate in itself. It says, hey, we're TypeCode. Can somebody please confirm this? They obviously went to Google Trust Services, and Google Trust Services says, hey, yes, we guarantee that you are TypeCode. And Google Trust Services, in this case, also is not a root certificate. They went to Global Sign and said, hey, can you please confirm that we're actually Google Trust Services? And Global Sign said, yeah, we confirm that you are Global Sign, that you are Google Trust Services. So what we need is this root certificate from Global Sign, which enables us to verify that every piece of the chain which we receive when we're connecting to TypeCode actually is valid, and in the end, it matches the root certificate from Global Sign. This root certificate can be obtained in a number of ways, depending on how this root certification authority provides it. In this specific case, they provide it as a CRT file on their website or on their servers. We obtain that one. You can use curl or whatever you want. Then we need to do the two last steps to get it into our source code here. First, convert it into so-called DR file. I once remembered what it means, and I forgot it again. Sorry. And then we can use the XXD tool from the Vim suite usually to put it into a header file. Then we just need to add inclusion guards. We can rename the structure, whatever we want. But at this point, we have the one certificate, which is crucial for our upcoming connection, ready to be built into our application. How do we use all of this together? Now, when we open the connection, we need to specify IP proto TLS 1.2. Everything before TLS 1.2 is considered broken and insecure by now. So we are verbally specifying, hey, this is a solid HTTPS connection now. In order to verify this, we need to say, this is the certificates that we know about. And we need to say, this is the host name that we're thinking we're talking to. That's why I said DNS earlier. If you're doing HTTPS, the certificate does not only mean, hey, there is a valid chain of trust. It means the string that you're thinking that you're talking to actually matches what is in this chain of trust. And this is being pulled together here via the TLS hostname and TLS peer hostname strings that we're expecting to match the actual chain. And now, also a complete new thing. We're not looking at a terminal, or at least partially. Remove this, make me big, give me VS Code. Why VS Code? Because, as I already mentioned, I have skipped a lot of error handling and infrastructure around the code, which makes all of this HTTPS things actually work. The two things that I really wanted to show is we pull in our certificate. It gets added to the certificate storage. Let me just find that. FTLS add. Where is it? Am I too stupid? I am too stupid. Obviously happens at some point in time. Here it is. The certificate, which we have in the header, needs to be manually added to the certificate storage on the device. Why is that? You could have more than one certificate. They could have different meanings. And last but not least, if you have a long-lived device, you might want to have the certificates not in the firmware, but somewhere else on other persistent storage, and you might be wanting to replace those because certificates have have lifetimes, and at some point in time they will get invalidated. They are sometimes very, very long, and sometimes really, really short. I think Let's Encrypt is at the moment chopping it down to just a handful of days or so. After that, as already showed, network management coming up, connecting to Wi-Fi. We're waiting for the IP address. And once all of this has happened, then we want to connect to HTTPS. Here is the things that I just indicated earlier. HTTPS path. This is like the tail that is relevant when talking to a REST API and the specific host that we're talking to. Again, the full code and all explanations will be in the show notes as tutorials. So the last thing I want to do is building, flashing, and running. Here we go. Very quiet today already. Probably everybody has either run off into Christmas holidays early or feels like HTTPS on Zephyr is not their cup of tea. But well, so be it. So we're seeing it built, it connected to the network, it got an IP address, DNS resolves things, creates TLS, connects, and here comes the answer. So full stack all the way from this tiny MCU all the way to a secure HTTPS connection is now working. Yay. I told you it's quite a story. The problem really is not opening a connection or connecting to Wi-Fi or whatever. The real challenge in this is certificates. Certificates and encryption are what makes this complicated. To highlight that again, if for whatever reason you do not need all of this, HTTP is super simple. You open the socket, you push some plain text through it, all's good. HTTPS, the S actually makes it like triple the size because cryptography and authentication are added, and you need a whole lot more RAM and storage for this. And the real challenge here is finding the right certificate, putting it into the device, making sure you can rotate it, all of this stuff. This is where the real magic happens. If you actually want to reproduce this right now, then I split this into 3 tutorials. First, adding Wi-Fi, then doing HTTP, and finally doing HTTPS on Zephyr on the ESP32. The links are obviously here in the video, which will not work for you, but I'll put them into the show notes. And this is somewhat based/derived from the Zephyr mainline example on HTTPS. The reason why I decided to pour it into a more specialized form is Zephyr, I already told you, it has a lot of subsystems and a lot of drivers, but many of the examples only work in a specific combination. And my impression is that this combination is often not the one that you have on your desk. So by declaring, hey, this combination that we're actually caring about is ESP32 S3 with Wi-Fi with HTTPS, I think the guide is really, really easy to follow. So you're all invited to check it out. With that, we're through. Happy festive season, happy change of year, I would say. Hopefully see you on the other side on the DeviceDojo session number 5. And there we will go back to Linux again with a somewhat weird topic. And I will talk about seccomp BPF and how it fits into a connected device. For that, that's today's DeviceDojo. Hit subscribe if you don't want to miss the next session, and drop me a comment below whether you've got questions about what we covered today or ideas for future episodes. I always love to hear from you. If you're ready to implement professional OTA updates in your own projects, of course, check out Mender.io, and all the links are in the description. And see you around in the next